Hello everybody. In this video we are going to derive the expectation and variance of negative binomial distribution. Before we start, let's have a look at this table. Depending on what x is counting, our probability mass function has different variations. In our case, we are going to use the top mass function here. X is counting the k failures until the experiment stopped, given our successes. Let's begin. Expectation for discrete random variables, by definition, summation x from 0 to infinity, x times probability mass function. In our case, we have this top function that x is counting k, so we're going to multiply k times p of k, and k from 0 to infinity. So k times the mass function, we said we're going to use the top function, which was k plus r minus 1 choose k, p to the r, 1 minus p to the k. And here k is starting from 1 to infinity. Because if we start from 0, that cancels out whole function. Now we're going to use the definition of combination and expand this. If it was n choose r, by the definition of combination, it would be n factorial over r factorial times n minus r factorial. So in our case, it will be k plus r minus 1 factorial over k factorial times k plus r minus 1 minus k factorial. And we have p to the r, 1 minus p to the k. Now k cancels k, we are left with r minus 1, the quantity factorial. Now we're going to expand k factorial as k times 1 less from k, k minus 1, quantity factorial. This is by the definition of factorial. And r factorial will be r times r minus 1 quantity factorial, and if you divide both sides on r minus 1 quantity factorial is equal to this expression. So that we're going to substitute this here, and we're going to substitute this for k factorial. So we have summation k from 1 to infinity, k times k plus r minus 1 quantity factorial. Instead of k factorial, we have k times k minus 1 factorial. And instead of r minus 1 factorial, we have r factorial over r. Here k cancels k, and some number over fraction, if you merge them, keep change flip, this r comes to numerator, r times k plus r minus 1, the quantity factorial, over, we have here k minus 1 quantity factorial times r factorial. And we have summation sign, k from 1 to infinity, p to the r, 1 minus p to the k. Now this expression is equal to k plus r minus 1 choose k minus 1 by the definition of combination. If you consider this as a, and if you consider this as b, it is like a factorial over b factorial times a minus b factorial. Let's see if it is. So k plus r minus 1 factorial over b factorial is k minus 1 factorial times a minus b is k plus r minus 1 minus k minus 1 factorial. And this k and negative 1 cancels here, so we are left with r factorial. And this is exactly the same as this. So instead of this expression, we can use this expression. And we can pull r to the front, summation k from 1 to infinity. Instead of this expression, we're going to use k plus r minus 1 choose k minus 1, and we have p to the r and 1 minus p to the k. Now we're going to make this expression look like our probability mass function, because we know that probability mass function, which is x from 0 to infinity, k plus r minus 1 choose k, here our counter is k, p to the r 1 minus p to the k is equal to 1, because this is the density function from 0 to infinity. All possible outcomes are summing. So we know that this expression is equal to 1. So we're going to make this look like our probability mass function. For this, we're going to use substitution. So let y be equal to k minus 1, and let z be equal to r plus 1. So if you solve for k in this equation, k will be equal to y plus 1. And if you solve for r in this equation, r will be z minus 1. Now let's do all necessary substitutions. We have r in front of the sigma sign. Now we're going to change our counter to y. When k is equal to 1, y equals to 0. If you plug in here 1, you obtain 1 minus 1, 0 to infinity. Instead of k, this k, we're going to write y plus 1. And instead of r, this r, we're going to write z minus 1. And we have negative 1 here. Instead of this k here, we're going to write y plus 1 again. And we have negative 1 here. P to the r, instead of r, we're going to write z minus 1. And 1 minus p to the k, instead of k, we're going to write again y plus 1. Now let's do necessary simplifications. Negative 1 cancels negative 1, and we can separate the powers here. So we can rewrite it as p to the z times p to the negative 1 by the power rule, and 1 minus p to the y times 1 minus p to the first power. And here we can pull this to the front. So we have r times 1 minus p over p to the negative 1 is 1 over p, sigma sign, y from 0 to infinity. We have y plus z minus 1 choose y, p to the z, 1 minus p to the y. If you realize that this is exactly the same as our mass function with different variables. So this is exactly equal to 1, because we're counting from 0 to infinity all possible outcomes of the density function. So this is 1. 1 times this is our expectation. So expectation is equal to r times 1 minus p over p. Now we're going to derive the variance. We know that variance by definition is equal to expectation of x squared minus expectation of x, the quantity squared. Here we're going to use expectation of x times x minus 1 plus expectation of x instead of expectation of x squared. This expression is equal to that. Let's prove that. If you distribute x inside, x times x is x squared, x times negative 1 is x, plus we have expectation of x. We know that expectation is linear, so we can separate it. Expectation of x squared minus expectation of x plus expectation of x, and if they cancel, so we see that this expression is equal to this expression. So we're going to use this expression minus expectation of x, the quantity squared, for the variance. For this, we're going to start with expectation of k times k minus 1 in our case. So this is by definition k times k minus 1 times the density function, which is k plus r minus 1, choose k, p to the r, 1 minus p to the k. Like we did in the previous section, we're going to expand this. So, and here summation is starting from 2 to infinity, because 1 and 0 makes this whole function 0. So k from 2 to infinity, we have k times k minus 1, and this is by the definition of combination. You can think it again like a and b. So it is going to be a factorial over b factorial times a minus b factorial. So we're going to obtain k plus r minus 1, the quantity factorial, over k factorial times k plus r minus 1 minus k factorial, which is going to be r minus 1 factorial again. And we have p to the r, 1 minus p to the k, the rest of the equation. Now let's start from here. Summation k from 2 to infinity. We have k times k minus 1. Here we have k factorial, that we're going to expand it k times k minus 1 times k minus 2 factorial. We go one more step because we need this for necessary simplification. And for r plus 1 factorial expansion, which is 1 less than from this, r plus 1 times less than this, which is r, times less than this, r minus 1 factorial. And if you divide both sides on r plus 1 times r plus 1 times r, you can see that r minus 1 factorial is equal to this expression. So this expression is equal to this expression. Instead of r minus 1 factorial here, we're going to use this expression. Okay, now we have k plus r minus 1 quantity factorial. Instead of k factorial, we're going to use this expression. So it's going to be k times k minus 1 times k minus 2 factorial. And instead of r minus 1 factorial, we said that we're going to be using this r plus 1 factorial over r plus 1 times r. And the rest of the equation is p to the r, 1 minus p to the k. Now we can cancel these, and some number over some fraction, we can merge them. So r plus 1 times r will be on the numerator. So summation k from 2 to infinity, we have r times r plus 1 on top, k plus r minus 1, the quantity factorial, over k minus 2 factorial times r plus 1 factorial. So we can pull this to the front of the sigma sign here, and this expression here is equal to k plus r minus 1, choose k minus 2 by the definition of combination. If we consider this is a and this is b, it's going to be like a factorial over b factorial times a minus b, the quantity factorial. And let's prove that this is equal to that. So k plus r minus 1 factorial, k minus 2 factorial, k plus r minus 1 minus k minus 2 factorial. And here k minus 2, k cancels k, and negative 1 plus 2 will be positive 1, so r plus 1, the quantity factorial. As you can see that this expression is exactly the same as this expression here. So instead of this expression, we're going to use k plus r minus 1, choose k minus 2. And the rest of the equation is again p to the r, 1 minus p to the k. Now we have r times r plus 1 in front, summation k from 2 to infinity, and instead of this expression we said that we're going to use k plus r minus 1 choose k minus 2, and we have p to the r, 1 minus p to the k. Now we're going to make this look like our probability mass function, because we know that probability mass function k from 0 to infinity, k plus r minus 1 choose k, p to the r, 1 minus p to the k is equal to 1, because this is the density function that is summing all possible outcomes. So now, since we would like this look like that, we're going to use substitution. So let y be equal to k minus 2, and let z be equal to r plus 2. From here, if you solve for k will be equal to y plus 2, and if you solve for r here in this equation, r will be equal to z minus 2. Now let's do necessary substitutions. We have r times r plus 1 in front of the summation. Here our counter will be y this time. When k equals to 2, y will be equal to 0. 2 minus 2 is 0. 0 to infinity. And instead of this k, we're going to use y plus 2. Instead of this r, we're going to use z minus 2. And we have negative 1 here. Instead of this k, we're going to use again y plus 2. And we have negative 2 here. P to the r, instead of r, we're going to use z minus 2. 1 minus p to the k, instead of k, we're going to use y plus 2. Now, negative 2 cancels negative 2. And we can separate the powers here as we did in the previous section. So p to the z times p to the negative 2, 1 minus p to the y times 1 minus p to the second power. So we apply here simple power rule. And here we are left with y plus z minus 1. Choose y. Okay. And we have summation y from 0 to infinity. And we have r times r plus 1. Now we can pull these expressions to the front. So we have r times r plus 1, and if we bring it to the front, it will be 1 over p squared times 1 minus p to the second power. Summation y from 0 to infinity, y plus z minus 1 choose y, p to the z times 1 minus p to the y. So if you realize that this is exactly the same as our probability mass function with different variables. So this is equal to 1. And 1 times that will be our expectation of k times k minus 1, which is r times r plus 1, 1 minus p the quantity squared over p squared. Now we're going to use this for our expectation of k times k minus 1. Let's go back to formula for variation. We said that variation is equal to expectation of x squared minus expectation of x. And we said that we can use the equivalent formula for this, which is expectation of x times x minus 1 plus expectation of x, and we have this one minus expectation of x. Now let's substitute everything. Expectation of x times x minus 1, we found this one. So it's going to be r times r plus 1, 1 minus p to the second power over p squared. In the previous section we found expectation already. That was r times 1 minus p over p, and this will be squared here, and this is going to be plus minus r times 1 minus p over p, the quantity squared, and that will be equal to our variance. Now all we have to do is just algebra. So we can factor out r times 1 minus p over p because we have this in all terms. So let's pull out r times 1 minus p over p. From the first term, we are left with r plus 1 times 1 factor of this 1 minus p over p, plus this whole term is taken out, so plus 1, minus 1 factor of this is taken out, r times 1 over p, 1 minus p over p. Now we're going to merge this p times 1 minus this numerator over the same denominator. So we have r times 1 minus p over p. We have r plus 1 times 1 minus p over p. P times 1 is p minus r times 1 minus p over p. Since we have the same denominator, now we can merge them. R times 1 minus p over p here, and we can distribute this likewise here and use the same denominator. So r times 1 is r times negative p is negative rp, 1 times 1 is 1, 1 times negative p is negative p, plus we have p here, negative r times 1 is negative r times negative p is positive rp. Now positive rp cancels negative rp, negative p cancels positive p, r cancels r, we are left with 1 over p. And if we multiply this expression by 1 over p, we're going to obtain r times 1 minus p over p squared. So this is our variance. I hope this video helped. Thank you very much for watching.